Hello everyone, for today's topic, we're gonna tackle about the reaction of aldehyde and ketones. If we're talking about aldehyde and ketones, they are actually very similar in terms of the molecule, in terms of the functional group. The only difference is where it shows up the functional group for an aldehyde or a ketone is a carbonate. Aldehyde and ketones are carbonyl compounds, meaning they contain a carbon-oxygen double bond. Their reactivity comes from the polarity of this bond, where oxygen is more electronegative, making the carbon electrophilic or electron deficient. Because of this, aldehyde and ketones commonly undergo nucleophilic addition reaction, where a nucleophile and electron-rich pieces attack the carbonyl carbon. Aldehydes have a hydrogen atom attached to the carbonyl group, making them more active, while ketones have two alkyl or aryl groups bonded to the carbonyl carbon, which make them slightly less reactive due to steric hindrance and electron donating effect. So let's begin in reduction reaction of ketones and aldehyde. So if we react the ketone or an aldehyde with sodium brohydride followed by H3+, at BH4 can reduce a ketone or an aldehyde into an alcohol. In this case, you're gonna get a secondary alcohol. Now, lithium aluminum hydride will have the same effect. So let's say if we react an aldehyde with lithium aluminum hydride, the end result would still be the same, and that is the carbonyl group will be reduced in alcohol.
Hello everyone, so we'll be discussing the continuation of the reduction reaction of ketones and aldehydes. Now let's get over to the mechanism of the first reaction. Here we have a ketone and we are going to react it with the sodium borohydride. So this is the drawing. As you can see, so the sodium ion has a positive charge. And the boron has a negative formal charge because it is attached to the 4 hydrogen atoms, and hydrogen is more electronegative than boron. So here's the drawing. Because boron has an electronegativity value of approximately 2.0, while hydrogen is 2.1. Thus, hydrogen is slightly more electronegative than boron. Now, the carbonyl atom of the carbonyl group contains a partial positive charge, and so this hydride ion with a negative partial charge is attracted to the carbonyl carbon. So this is the drawing. So it attacks it, and this is going to give us alkoxide, which has 3 lone pairs and a negative charge, and the added 8 hydrogen. So here's the drawing. As you can see, now we are going to react the alkoxide ion with the H30+, and so it's going to pick up a hydrogen. So here's a drawing. And lastly, and turn it into a secondary alcohol, and so that is the mechanism of this reaction.
Good morning guys, I will discuss the reduced amination that it converts ketones into an amines. So I will show you the examples on the screen. So first, we're going to react it with ammonia, and this is going to give us an amine. So water is a side product you need to take away. So the oxygen and two hydrogen atoms from the nitrogen atom, which leaves behind one hydrogen. So now we have the imine product, and then we can reduce the amino using the hydrogen and palladium over carbon into an amine, and so that process. The conversion of a ketone into an amine is reductive amination. That's all. Thank you.
So let's talk about the reactivity of aldehydes and ketones. From aldehydes is more reactive than acid aldehydes, and acid aldehyde is more reactive than propanol. So aldehyde is more reactive than ketones. The reason why ketones is less reactive, for one, we have these CH3 group, which hinders nucleus fusion, and also these CH3 groups are electron donating groups. So they don't need electron density to electrophonic carbonyl group, making in the last electrophilic, and so that's why ketones are less reactive than aldehydes, is due to steric effects of the CH3 groups, and also the fact that they don't need electron density to the carbonyl group. Okay, let's see if its react from aldehyde. Reform from aldehyde is highly reactive towards water. And it's going to form like this. And that's why we have the big arrow towards the right. And now, if we think this acid, aldehyde, unreactive from water, unreactive from water, this reaction is like this. And get like this. And now, the ketone is not really reactive of water, so ketone are less reactive to water and the nucleus spouse than aldehydes. So as you can see, from aldehyde we're virtually completely converted to the high dry form in only very small amount of who stay in that aldehyde form. So while acid aldehyde will exist in the significant amount, the ketone is really doesn't want the react of the water.
Reduction of aldehyde and ketone chlorides using sodium borohydride. Aldehydes and ketones, these contain a carbonyl group. Aldehydes have one hydrogen attached to the carbonyl carbon, while ketones have two carbon groups. If a chlorine is present, it could be part of an acyl chloride or somewhere else in the molecule. Sodium borohydride is a reducing agent, meaning it donates hydride ions to reduce the carbonyl group. If you have an aldehyde or ketone with a chloride somewhere in the molecule but not in the carbonyl group, sodium borohydride will only reduce the carbonyl group to an alcohol, and the chloride will stay unchanged. If it's an acyl chloride, sodium borohydride is usually not strong enough to reduce it directly, but it can sometimes work under certain conditions. A stronger reducing agent like lithium aluminum hydride is typically needed for acyl chlorides. Example, reduction of a ketone with a chloride group, 4-chlorobutanone, and react it with sodium borohydride. This structural diagram shows the reduction of 4-chlorobutanone with sodium borohydride. The ketone, or the carbonyl group, is reduced to an alcohol while the chlorine remains unchanged. Sodium borohydride reduces aldehydes and ketones to alcohols. If a chlorine is attached elsewhere, not in an acyl chloride, it stays unchanged. Sodium borohydride is usually not strong enough to reduce acyl chlorides.
Reduction of an acid chloride into an alcohol. When we reduce an acid chloride to an alcohol, we are turning one kind of molecule into another by adding hydrogen and removing chlorine. Here's a simple breakdown. What's an acid chloride? It's a molecule that has carbonyl group and a chlorine atom attached to the carbon. How does reduction work? Reduction means adding hydrogen to the molecule. For this, we use a substance called a reducing agent, like lithium aluminum hydride. The reducing agents add hydrogen to the carbonyl carbon and the chlorine atom leaves. What happens during the process? First, the acid chloride turns into an aldehyde, which has CO and hydrogen atom attached. If we keep adding hydrogen, the aldehyde changes into an alcohol, which has a COH group. So here's the example. If we start with acetyl chloride with CH3, CHO. So here's the structure of the acetaldehyde. It turns into acetaldehyde with CH3CHO. Then with more hydrogen, it turns into ethanol. And here's the structure of ethanol. CH3, CH2, and OH, which is alcohol. Example number 2. If we start with formyl chloride with HCOCl, it turns into formaldehyde, HCHO. Then with more hydrogen, it turns into ethanol. The structure of methanol is CH3OH, which is alcohol. We do this reduction to change one compound, acid chloride, into something useful like alcohol, which can be used in making other chemicals or products.
Hi, I am Crisanne Pogoso. I'm here to discuss the last topic, which is the type of reaction of ketones and aldehyde. And this reaction is all about Grignard reaction. So first, I will explain to you what is Grignard reaction, the explanation of Grignard reaction to aldehydes and ketones and how they react. So, a Grignard reagent is an organomagnesium halide, a type of organometallic compound where a carbon atom is bonded to a magnesium atom, which in turn is bonded to a halogen like chlorine or bromine. So, reaction with aldehydes and ketones is the carbonyl carbon in aldehydes and ketones is electrophilic, electron deficient due to the electronegative oxygen atom. The carbon atom in the Grignard reagent is nucleophilic electron rich due to the partial negative charge in the carbon atom bonded to magnesium. The nucleophilic carbon in the Grignard reagent attacks the electrophilic carbonyl carbon, forming a new CC bond and creating an alkoxide intermediate. This intermediate is the protonated usually with an acid to form an alcohol. So this picture is the reaction mechanism with aldehyde and ketone. So nucleophilic carbon atom present in alkyl or aryl radical R attacks the carbonyl group C equals O through single electron transfer to form an organometallic intermediate. Protonation of alkoxide oxygen in the intermediate in presence of water forms primary alcohol with formaldehyde, secondary alcohol with other aldehydes R equals H, and tertiary alcohol with ketones. So the K player is the Grignard reagent, an organometallic compound with a general formula RMGX, where R is an alkyl or aryl group, methyl, ethyl, and phenyl. And the Mg is the magnesium. X is a halogen, usually bromine or chloride. Grignard reagents are strong nucleophiles, meaning they are electron-rich and readily attack electron-deficient center. So the carbon atom attached to the magnesium in the Grignard reagent is the nucleophilic center. When a Grignard reagent encounters an aldehyde or ketone, the nucleophilic carbon attacks the electrophilic carbonyl carbon. So this is the second picture, the Grignard addition to aldehydes and ketones, how it works. The nucleophilic pair of electron in the CMG bond attack the carbonyl carbon, breaking the CO bond. In the second step, a proton source is added in workup. So in step 1, this is the addition, and this is the step 2 of protonation. So take note that addition is the most important mechanism for carbonyls. Carbonyl carbons are electrophiles and will react with many different nucleophiles. So this is the example of Grignard reaction, addition to Grignard reagent to aldehydes. Example is reaction of propanol and aldehyde with a methyl magnesium bromide Grignard reagent is propanol plus CH3 MgBr2 2-butanol as secondary alcohol. So these are the specific example and how it works. So Grignard reaction must be carried out under anhydrous conditions. Water reacts with Grignard reagent, destroying them. The Grignard reagent is a strong base, so it can also react with acidic protons and alcohols or carboxylic acids. The Grignard reaction is a versatile tool for building complex molecules and is widely used in organic synthesis. So this explanation provides a simplified overview of the Grignard reaction. The reaction mechanism can be more complex depending on the specific reactants and condition. And that's all. Thank you.
Oxidation of aldehyde and ketones. Oxidation is an important chemical reaction that helps in the transformation of the organic compound into a more oxidized form. Let's explore how aldehydes and ketones behave under the oxidation condition and how their molecular structure changes during the process. Oxidation of aldehydes. Aldehydes are highly susceptible to oxidation due to the hydrogen atom attached to the carbonyl carbon. When aldehydes undergo oxidation, the carbonyl carbon gains an oxygen atom, forming a carboxyl functional group, which converts carboxylic acid. This reaction can be carried out using different oxidizing agents such as the filling solution, where the copper ions are reduced to copper oxide, forming a red precipitate as the aldehyde is oxidized to a carboxylate. Another example is when ethanol is oxidized, it forms ethanoic acid. Oxidation of ketones. Unlike aldehydes, ketones are more resistant to oxidation because they lack the hydrogen atom attached to the carbonyl carbon. Instead of a simple oxidation, ketones undergo cleavage when subjected to strong oxidation condition. This means carbonyl bond breaks for smaller carboxylic acid. Common oxidizing agents for ketones include potassium permanganate, where it breaks the C-to-C bond adjacent to the carbonyl group, resulting in the formation of smaller carboxylic acids. For example, 2-propanone is split into acetic acid and formic acid. In summary, aldehyde readily oxidize to carbon acids by the addition of oxygen to the carbonyl carbon, while ketones require strong oxidation condition to undergo cleavage, forming smaller carboxylic acid. These oxidation reactions are useful in both laboratory tests and industrial application, such as production of carboxylic acid and esters. Understanding these structural changes help in the identification and functional transformations of carbonyl compounds.